Welcome to the satellite communication course. Today we will learn the satellite link design. So satellite link design means what? How your satellite communicate to the earth station or earth communicate to the satellite there. So that we have learned today. So that is about a link design. In the case of a satellite link design, we should know that for a given earth station, we say that how your satellite responding to the satellite here. So this one is about we have the antenna here. So this one we can say that is about a uplink means that uplink we can say that this one is about earth station, this one is about we have a satellite here. Now how this satellite send the signal to the earth station, here we can say that this one is you can say it is about a uplink, and a satellite send the signal to the earth station, that will nothing but the downlink here. Now in the case of a link design, how your satellite send the signal to the earth station, or how your satellite receive the signal from the earth station. So means that will be the quality of signal received by the satellite from the earth station, or a quality of a signal received by the earth station from the satellite. So we need to know about what will be the uplink and what will be the downlink here. So then we say that is about a quality of a signal. That quality of a signal, it is depending upon that what will be the power transmitted. Okay, we can say that is about a transmitted power. So transmitted power, if it is a uplink design, we should know that what will be the transmitted power from the earth station. That will be uplink. So that transmitted power is nothing but what? What will be the effective isotropic radiated power generated by an antenna? Alright, that is about a transmitting power. Then we say that a power transmitted by that antenna. So that's why we should know that the gain of an antenna. Okay, gain of an antenna. In that case, that gain of an antenna is nothing but for the receiving gain, or you can say that is about a transmitting gain of an antenna. Means gain at a receiver and gain of at a transmitter for the given antenna. So next we need to know about from this earth station to the satellite. So this one is about a path from earth station to the satellite signal is propagating. So in that case we should know that what will be the path loss. So in between that, this one is nothing but a atmospheric region. That in that atmospheric region, the gases molecules, ion molecules are present, as well as in a rainy season. So there may be a cloud. In that case, what happened on this transmitted signal or a received signal? Okay, what happened? Why? Because of that particular gas molecules or ions and that particular cloud there. So we need to know that what will be the loss by those molecules. And again, the other losses, that other losses belongs to that noise at a receiver or a loss at a transmitter or and a receiver there. Okay, that other losses we need to know, or for a given particular system, so what will be the loss. So in ideal condition we say that there is no, in atmospheric condition, if it is the ideal one, so no gas molecules or no cloud is there. So in that case, how much will be the signal to noise ratio there? So in the case of a earth station transmission signal and a satellite here, so we can say that instead of a signal to noise ratio, we can express in terms of a carrier to noise ratio. For the transmitting signal or for the uplink, what will be the C by N ratio, and for the downlink, what will be the C by N ratio. And then when we say that data is transmitting from the earth station, so what will be the scheme of a modulation used so that we can occupy large number of a channels, or that capacity or bandwidth will be increased here. So now these are about the fact that we should know regarding the quality of a signal in the uplink or a downlink here. So that is about a signal quality. Then again, we need to consider other parameter too. That parameter is nothing but what? What will be the size of an antenna? That size of an antenna for the transmitter or for the receiver too, and how much is the power to be transmitted, expected power, how much is the power to be transmitted. And then we should know that what will be the noise figure of the front end amplifier in the receiver that is to be selected. So that's why we should know that a noise figure here that will be for the given amplifier. And then what are the various techniques that is about for the communication. So we say that a modem's used for a given application. So then we say that here in earth station as well as in a satellite, that single antenna used for the transmitting as well as the receiver. If the single antenna is used, then what component is used so that that same antenna can be used as a transmitter as well as a receiver. So that component is nothing but what? It is about a duplexer. And that duplexer should isolate, or the role of a duplexer is to isolate the transmitter and a receiver signal. Okay. Means single antenna can be used as a transmitter as well as receiver. So that's why role of a duplexer is to isolate your transmitting and a receiving signal. That will be the role of a duplexer here. So generally the duplexer is nothing but a three-port device. So that is nothing but a circulator. Generally we say we have the single component can be used as a transmitter or a receiver. Suppose this one is a transmitter here. So your signal will goes to the antenna here. This is about a antenna now. Whenever the signal received, that will go to the receiver. So that is about a rule. So generally it is about a three-port device, and this one is a passive device. This one is a three-port device as well as a passive device. And the ferrite material is used in such a way that that will select a particular RF frequency so that it will propagate signal in a one direction. So if you see that a transmitter, the signal is transmitting toward the antenna only, so no signal will transmit it to the receiver here from this transmitter. So that transmitter and receiver isolates here. Even if we are receiving the signal, in that case, that antenna receiving the signal that will direct it toward the receiver here. So no signal directed toward the transmitter here. So that is about your role of a duplexer here, or we can say that that role of a duplexer is just like to use to isolate the transmitter and a receiver here. Then how you are feeding the antenna from this particular transmitter, and how much is the power requirement. That is about, you can say, a power transmitted. So then that particular, that, because at a transmitting side we require a large power is to be transmitted, because that signal is to be reached to the satellite. So that's why the large power is to be transmitted. When we transmit the large power from this transmitter, so that large power should not reach to the receiver, because a receiver has a low power amplifier, or you can say that low noise device, LNB, or a low noise amplifier there, and that input is low as compared to the whatever the transmitting power. So that's why that isolation is to be there. Even if supposed to be small leakage is transmitting from the transmitter to the receiver, so then receiver may damage. So it avoids that leakage to be transmitting here, and that receiver is to be isolate from the transmitting signal. So now basic satellite communication model, we say here we have only a single earth station and a satellite, but it is not a single earth station. There can be a multiple earth station that will communicate to the satellite. So that's why a multi-channel communication takes place, and then a technique is used to access this particular earth station from the ground. So that will be a multiple access technique. So we'll see that in a multiple access technique in detail. So before that, we should know that what will be the communication system model. Generally, we have a multiple earth station 1, earth station 2, then we have the earth station n number of a earth station. And then each and every earth station, they are transmitting the signal. We can say that they have the transmitting antenna. They are transmitting the signal, and then that selection of the signal from the each and every earth station, that will be depending upon that a multiple access technique, and then all the signal will be uplink here. Okay, we can say that there are the multiple earth station here, multiple station that will transmitting the signal, and then we have the generation of a uplink signal, or we can say that that will be combined at the satellite. Likewise, when we have the this one, we have the transponder there. So in the case of satellite transponder, so it receive the signal. They have a low noise amplifier here. Then it will be down convert the signal, and then after that we have the high power amplifier, and then it will transmit it. Then again that signal will reach to your whichever the downlink mechanism, and then it will be transmitted to the earth station 1, earth station 2, then we have the earth station n. So multiple earth station, so your signal will be reached. Now there are the lots of Earth station they are transmitting, and the satellite is accessing many Earth station. That many Earth station that will be visible or that will be in the range of the satellite here. So that's why we can say that Earth station, multiple Earth station, they can communicate to the satellite. Both have the uplink and a downlink there. So this means multiple Earth station they can transmit and receive signal, and they can share the resources of the satellite. Means we can say that a satellite have some particular bandwidth of that particular transponder. So that bandwidth will be shared by the multiple Earth station. So now how these multiple Earth stations are communicating? They are using simply a multiple access technique to connect the multiple Earth station. So that multiple access technique in which we can consider that they are sharing the bandwidth as well as they are sharing the time, they are sharing the power. So then whichever the signal received by the satellite from the Earth station, so then they have the low noise amplifier, and then the down conversion, and after that it will be transmitting to the Earth station there. So the role of the receiver here in the case of a satellite, so they are to distinguish each and every signal from the Earth station, or according to that the transponder respond, and then that will be transmitting to the Earth station there. So even in the receiver at the Earth station, they have similar kind of a setup. They have the low noise receiver. Similarly, they have the frequency translator. They have a local oscillator. Okay, likewise, same. How your satellite they have this component of low noise amplifier, down conversion, high power amplifier. So similarly, at the receiving Earth station, they have the same component, similar component, and this component at a satellite that is nothing but a sub-satellite component, or you can say that sub-component of a satellite there. That is a nothing but a transponder here. So the transmitting the signal and receiving the signal using the same antenna. So that's why the duplexer is there to isolate the transmitting signal and a receiving signal. Now, in the case of a satellite link, we should know that how much is the a transmitted power. Means we can say that from the Earth station to the satellite, how much is the power transmitted by this Earth station. So that transmitted power is depending upon that gain of a transmitting antenna. And then what will be the distance we should know. And then again at a receiver, what will be the gain of a receiving antenna. So power transmitted by the Earth station, power received by the satellite, then we will get that uplink component. And then we can calculate that a carrier to noise ratio for the given uplink. So similarly, we can calculate that a carrier to noise ratio for the receiver, and we can say that a performance of a satellite link that will be depending upon that what will be the uplink and a downlink power, or you can say that what will be the carrier to noise ratio for the uplink and a carrier to noise ratio for the downlink. So to understand that what will be the carrier to noise ratio, we should know that what will be the antenna gain. Means at a transmitter side from the earth station, what will be the antenna gain here, so that in a earth station they have the power amplifier. So that power amplifier will receive the sorry that produces the that much power, so that antenna will transmit the signal there. Okay, so we should know that first what will be the antenna gain here. So antenna gain for the transmitting antenna, or you can say that antenna gain for the earth station. So generally a transmit antenna that will provide the gain, and that will gives us the output power, and that will be transmitted in space there, so that satellite will receive the signal there. But before that, eh, they have the power amplifier, and after that there will be antenna. So then what will be the output of a power amplifier? This will be the power amplifier output, so that that antenna will deliver the some particular output power. So that's why we should know that the gain of that antenna, so power amplifier output supposed to be consider that a transmitted power is about a PT, and that is nothing but a transmitted power, or you can say that is about a output power of a your amplifier there, and then gain of your transmitting antenna, and then that transmit the signal, because we should know that for the given antenna, so what will be the radiation pattern, and what will be the directivity, in which direction your signal is going to be transmitting. So that's why the maximum gain achieved by the antenna in the given direction. So generally we consider that a isotropic radiator, and that radiate the signal in all the direction, and they have the solid angles of what we can say a 4 pi of a radians. That is about a beam solid angle. So that's why if you consider the radiation pattern of a point source, so that is nothing is a point source, it radiates the signal in all the direction. So means this radiation, it looks like in a spherical shape or a sphere, and that for the given particular sphere they have the surface area of a 4 pi r square. That r is the radius of this particular sphere. Means you can say that this one is about, you can say it is about a point source, and from this point source this one is a radiation pattern, and this one is the distance that is called as a r here, and the surface area is nothing but a 4 pi r square. So from that we can calculate that what will be the power density. So flux power density at some particular unit area in the particular, this one is a sphere, or from this isotropic radiator. So flux power density is nothing but F, sorry, flux power density, that is equal to F. That F is depending upon that how much is the power transmitting, by the amplifier. Okay, we have the amplifier, and that will give the out that will deliver the output to the antenna. Okay, means from the amplifier that will be the antenna there. Okay, we can say that high power amplifier, that is about a transmitting power, and then that will gives to the antenna here, and then antenna transmit. So antenna has the gain of a GT. The input to the antenna is that about a GT. So flux power density is nothing but F is equal to what? What will be the transmitting power for a given particular source in the given region there, 4 pi r square. So for a given equator, that is about, you can say, we have for a given particular point source at one particular place, or if you consider the earth surface here, so on the earth surface, if you consider that, we have the equatorial plane, or on the equator, suppose we have the transmitter there. So how much is the region covered by this particular antenna there? So supposed to be this particular point source is present on the equator, and then how much is the transmitting power there? So in that case, at some particular point, we can calculate that how much is the power transmitting. For the point source, transmitting power is PT here, and that at some particular place, we say is about a distance, so that we can calculate that power flux density. So now, if we consider the gain of an antenna, so for the gain of an antenna, we should know that what will be the bore side. So in which direction? Okay, bore side. This is nothing but a main lobe. We have a side lobes. Likewise, we have a back lobes too. So this one is about a main lobe here. So we have a side lobes too. Okay. But even if you consider that, in which direction it delivers the maximum power, that is nothing but a bore side of an antenna. And from that, we can calculate from the maximum, we can calculate the 3 dB point, and that line joining this 3 dB point, and that will gives us the 3 dB beam width, or you can say that is about a half power beam width. And this one is nothing but a 3 theta here, means your power radiating maximum power in the given direction. So power of this particular P of theta means it is about the power transmitted by the given antenna in a theta direction, and that will gives us the gain of an antenna. So gain of an antenna is nothing but what will be the power transmitted in the theta direction by an antenna with respect to what will be the power transmitted by an isotropic radiator in same direction. Okay, in the theta direction. So generally, a isotropic radiator, if you see that, radiate the signal in all the direction. So that's why a point source is nothing but that isotropic radiator. So for the isotropic radiator, we can consider that area for the, that is about a 4 pi radians. So that's why the gain of that antenna g of theta is equal to power radiated in the theta direction with respect to what will be the power by the isotropic radiator, and That is about a 4 pi radian there. So means a gain of that antenna is nothing but what? So that radiation in the given direction or a maximum power in the given direction or higher concentration of a power in the given direction, and that will gives us the gain. Means maximum concentration is nothing in a bore site of an antenna. So that's why that gain of the antenna we can find out from the bore site of an antenna. Means we say that here, so theta is equal to 0 suppose, then in that case toward the bore side, then instead of g0 g theta, that will be of a g of 0 here. But generally we consider that in a given particular direction how much is the power transmitted by this antenna there. So we consider the bore site of an antenna. So that's why we should know that what will be the radiation pattern of the antenna, so that we can calculate that where will be the or in which direction we are getting the maximum power, so that we can calculate that bore site of an antenna, or we can calculate that what will be the beam width of the antenna there. So if we consider the antenna here, so gain of an antenna can be calculated, because we can say that it is in with respect to that aperture size and all. So we can calculate that a gain of an antenna with respect to the what will be the area, aperture area of an antenna there. So for that condition we should know that what antenna structures we are using, and what will be the operating wavelength of that particular antenna. So we can calculate the gain, that is 4 pi into A in the given region with a respective wavelength. And if you see here, A is nothing but what? That is about the aperture area of an antenna, and this one is about a your operating wavelength or wavelength of the whichever the signal we have, and that will transmit in the to the given particular direction. So generally we say that when we provide the input from this amplifier to the antenna, so all power will not be transmitted in the given direction. So here generally we can say that even if in the calculation of a gain we consider only the main lobe, and this one is back lobe and side lobe we are not considering. So if whichever the power applied to the antenna, that all the power will not be radiated by the antenna. So that's why we should know that what will be the effective aperture area or effective radiating power by this particular antenna there. So that's why the efficiency of an antenna is depending upon that what will be the effective area, what will be the effective area, and what will be the actual area of that antenna there. So that will gives us the AE by A here. So this is about the actual area of the aperture, and this one is about the effective area of the aperture. So effective area of the aperture means what? What will be the effective radiation takes place by this antenna there. So how much is the power generated by the antenna? It is depending upon that effective area of an antenna. So that's why we can rewrite the equation or a term of a gain with respect to instead of a area or aperture area, we can write the term that will be the effective area with respect to lambda square. And that effective aperture area, if we calculate, that is about Na here. So we will get the equation in terms of Na, that is a, we can say that the efficiency of an antenna, okay, if that is about efficiency of an antenna with respect to that, what will be the actual area of the antenna with respect to lambda square. And this one is about the gain of a given antenna. So from that, we can calculate that what will be the effective isotropic radiated power of an antenna. Okay, what will be the effective isotropic radiated power transmitted by this antenna? So here that is about a GIR. So when we consider the gain, then we need to consider that for the given particular gain of an antenna, so we should know that what will be the aperture area of an antenna. Suppose if you consider that antenna is about a circular aperture, or that circular aperture is nothing but what? We can say it is about a parabolic dish. If that particular circular aperture area or circular aperture if we are using, or a parabolic dish if we are using this one, okay, so that is about your circular aperture area of an antenna here. Likewise, supposed to be if it is a circular in shape, that is about a aperture. So in that case, that area can be expressed in terms of what? What will be the diameter of this particular circular? That's the area is equal to 4 pi d square by 4 here. Okay, this one is about a d. Here is nothing but a diameter of an antenna. This one is about a circular antenna. So that's why we can write a gain with respect to aperture or antenna efficiency here. Then aperture area 4 pi a, I think this one, 4 pi a divided by lambda square is equal to, we can rewrite in terms of whatever the circular antenna here or circular aperture here. Pi square d square divided by lambda square, or we can rewrite the term that will be a pi d by lambda bracket square. That is nothing but the gain of an antenna. Okay, this term is nothing but the gain of an antenna here. So we should know that what will be the antenna type. Generally for the earth station, it is about a parabolic dish is to be used as a transmitter. So that's why the most of the cases this antenna is to be used here. So that gain is like that. So then next term, we should know that what will be the effective isotropic radiated power, EIRP. Means radiated power. Okay. So now in this case we can say that a radiated power of an antenna by an antenna in a given direction. Radiated power by an antenna in a given direction. So now this is about the gain of an antenna. If we consider that a circular aperture there, so we should know that what will be the radiated power in the direction of a main lobe of an antenna. That is about this one is about a main lobe of an antenna. This is about a radiated power. So generally we consider that a omnidirectional radiation pattern, but in the case of uh, omnidirectional antenna, we should know that what will be the effective isotropic radiated power. So in that case, EIRP is nothing but effective isotropic radiated power. So that will be nothing but a power transmitted, okay, into a gain of an antenna. So gain of an antenna, that antenna which we are using for the transmitting here. So that's why power transmitted into the gain of an antenna, and that will be nothing but what, a PT into GT, and that will be power is in terms of watt here. So gain is not just like a term here. It is nothing but a PT into a GT here. So then ARP is equal to what? A PT into GT, that is nothing but a watts here. And if we express that in terms of a dB, AIRP in terms of a dB, so then AIRP terms of a dB, that will be again a dB watt here. So power transmitted, that will be in terms of a dB watt plus gain of a transmitting antenna in a dB. So this gives a radiated power in a dB watt, and here we consider that a power transmitted in a dB watt. So we need to convert in terms of a dB. So if supposed to be some term is given in terms power is given x watt here, and we need to convert it into a dB. So we just convert that 10 log of whatever the x watt of a power with respect to 10 here, that will be 1 watt. If it is a milliwatt, dBm, so milliwatt. Okay, if it is a dB microwatt, so microwatt. Likewise, so we can convert that in terms that power in a watt, dB watt, or a dBm, or a dB micro there. So that is about your effective isotopic radiative power. Then we should know that a flux density power for a practical radiator. Now, generally, we have seen that a flux density at some particular distance r from a power radiator is nothing but what will be the power received in that particular unit area from this point source. This is nothing but a unit area from the distance from the source to this particular region there. Okay, so this is about a point source. This is about a power radiator, and for this particular power unit area, we can calculate the flux density. But in the case of a earth station, or we can say that for a practical radiator, the total power radiated, that will be given by in terms of a EIRP, effective isotropic radiated power. So total transmitted power means nothing but from the source, it is nothing but it transmits the power, that will be effective isotropic radiator, and at a distance r, So that's why the flux density, okay, the flux density or power flux density we say is nothing but F is equal to AIRP divided by 4 pi R square. We know that AIRP is nothing but what? PT GT divided by 4 pi R square. That is about watt per meter square. Because this one is about the area isotropic radiator, or you can say that the transmitting power, it is about a circular shape. So that's why 4 pi radian for the circular shape here. And R is the distance